Hi everyone. This is the 5.1 quiz review. I'm just going to go through all 8 problems and just show you how to do them. So that way you can take the retake and hopefully improve your score. So I don't know if you guys had the same order questions. I forget if I shuffled the order of questions or not, yeah. So the first question I have is which wave arrives at point B? So this is a reading from a seismograph, which is the tool that measures seismic waves. So this whole thing with all these big bumps, that's an earthquake. This stuff here, where it's not very large, this is noise. That's normal vibrations that happen in Earth all the time. But A and B, point A and point B, those are the earthquake waves. When an earthquake hits, there are two different waves. There are P waves and S waves. They get their names based on which one happens first. P stands for primary, and S stands for secondary. Primary means first, secondary means second. So which wave arrives at point B? Well, A, this is the first wave, so this will be the P wave. And point B, that's the S wave, because it happens second. Okay. Let's go down number 2. Which type of seismic wave will not go through liquids? So we just said that there are P waves and S waves. Okay, this should have came straight out of your notes. P waves are the compression waves, and S waves are transverse. And we talked about how compression waves are not picky. Therefore, compression waves will go through solids, liquids, and gases. Okay. But a transverse wave is picky. Just like an ocean wave will only work in the ocean. It crashes and ends when it reaches solid ground. So it only goes through liquids. It's picky. The S wave from an earthquake will only go through solids. It's a different type of transverse wave than an ocean wave, but it has the same idea. Transverse waves are picky. Therefore, the transverse wave will not go through liquid. Okay, so now we're looking at this little graph and we're trying to figure out what is the amplitude. So you should know that amplitude is the distance from center line to trough, or center line to crest, or center line to trough. What I said was correct, I was just labeling the wrong part. So what is this distance? Well, it goes up to this line here, and there's 1, 2, 3, 4. 1, 2, 3, 4. So that would be 4 meters because it goes up 4 on the number line. And this is amplitude. Okay. Number 4, what is the distance for one wavelength? So wavelength you measure from crest to, oh my goodness, I did it again. from crest to crest or trough to trough. Okay, so in either case we have, so we go from negative 270 all the way to 90, or the other way around, negative 90 to positive 270. So to go from negative 270 to 0, we have to basically, to get from here to here, we add 270. To get from here to there, that's another add another 90. 270 plus 90 gives you 360. So the distance is 360. Okay. Okay. All right. So a computer monitor has a frame rate of 120 hertz. What is the period? Okay, so remember, hertz, this is the measurement for frequency. And period is denoted by capital T. Okay, period is equal to the number of seconds or the amount of time that goes by in one cycle of a wave. Whereas frequency, which is a fancy F, is the number of cycles per second, per 1 second. Okay, so you can see that really all we did was just flip what's on top and bottom. And so what that means, like mathematically, is that frequency is equal to 1 over period, or period is equal to 1 over frequency. Basically, all you need to do is flip the number. So if we have a frequency of 120 hertz and we need to find the period, we can just use this equation here. Essentially just flip this number upside down. Okay, so the period is equal to 1 over 120 hertz. If we plug that into a calculator, .008. There we go. All right, so doing it the other way around, we have a ball with the period of 0.5 seconds. We are looking for frequency. Okay, so how do we do this? We just need to flip that upside down. We need to flip this number upside down. So frequency is equal to 1 over the period. Frequency is equal to 1 over 0.5 seconds, which if we plug that into a calculator, gives us 2. Okay, what is the wavelength here? All right, so again, you can start from crest to crest or trough to trough. You could do center point to center point, but you just have to make sure that they are like matching center points. So like this is a rising center point because it's going from under to above, it's going up. You couldn't do here to here because this is a falling center point. Okay. So the center points would be the easiest way to do it here. But let's look at from crest to crest. Okay, so we're in between two lines. 1, 2, 3, 4, 5. So this goes from 1, that's 1.5, to 5, 6, 7, 7.5. Okay, so 7.5 minus 1.5 is equal to 6. Okay. Let's just look at that again one more time. So we're just going to count these up. Here's 1, here's 2, 3, 4, 5, 6, 7. So we're in between 1 and 2, which gives us 1.5. And over here we're between 7 and 8, which gives us 7.5. The distance between 7.5 and 1.5 is 6. All right, last one. A musician turns up the volume on his speakers, or on her speakers. What did she change about the wave? Okay, so I know we talked about this in our notes, but just to reiterate, wavelength slash frequency are the identity. Sorry, I can't spell. Are the identity of a wave. Okay, so these are what make a wave. These are what makes a wave a wave. For example, every note in music, I don't know how many lines it's supposed to have, but that's not the point. So for example, if you're playing a C in a certain octave, that C, no matter what instrument you're playing, has the exact same frequency. Let's say that a C is a frequency of 250 hertz. That is the identity of a wave. If you were playing something with 500 hertz, that would be a completely different note. You can't change frequency without changing the wave that you are making. Okay, same thing applies with light. So that was a frequency example, which frequency and wavelength are very related. When you change frequency, you do end up changing wavelength, just FYI. So if we're talking about light, like red light has a wavelength approximately of 550 nanometers. You can't change that wavelength without changing the colors. If you went down in wavelength, made the wavelength shorter to, I don't know, let's say 300 nanometers, that would be ultraviolet light, I think. I think that's ultraviolet. If you go down far enough, you're getting into ultraviolet light, essentially is what I'm trying to say. I don't remember the exact numbers, but the point is the same. Wavelength and frequency is the identity of the wave. Let's say that this is a D. Okay. So it cannot be, the answer to this question is not wavelength or frequency because those are identity of the waves. All she's doing is playing louder. Well, let's think about what other properties of waves do we have? We have period, but period's essentially the same thing as frequency, just upside down. So again, period is identity of a wave. What about amplitude? Well, we talked about amplitude is the distance from center point to crest or center point to trough. When you increase it, you are increasing the intensity of the wave. So I know this is the correct answer. In sound, increasing amplitude increases loudness or volume, okay? If you increase the amplitude of light, then you are increasing the brightness, okay? So amplitude, you can change the amplitude without changing the wave. You can make a C note louder by increasing the amplitude. You cannot change the wavelength or the frequency without changing the note you're playing, but you can change how loud you play it by making the amplitude greater or smaller, okay? And that's it. That's a quiz, so hopefully this was helpful for you, and yeah.